This PowerPoint is for the AMS Weather Studies course, WE 101 at Mohawk Valley Community College. This is Chapter 6, which is going to deal with humidity, saturation, and atmospheric stability. This PowerPoint is going to deal with a number of things relating to water in the Earth-atmosphere system, including global water cycle, content of water, how we monitor water vapor, how air becomes saturated, and something called atmospheric stability and the lifting process. Atmospheric rivers is a recently coined term that describes a narrow band of concentrated water vapor that's generally transported in the lower atmosphere and is responsible for much of the horizontal flow of water vapor outside of the tropics. These atmospheric rivers are essential contributors to the water supply of the West Coast states in the United States and basically deliver somewhere between 30 and 50% of the annual average precipitation by about a dozen or so of these atmospheric rivers in the western part of the United States. Typically, these ARs are centered in the lower troposphere at about 10,000 feet above the Earth's surface. They have a width of about 500 kilometers or about 300 miles and at least 2,000 kilometers or about 1,200 miles long, sometimes winding over entire ocean basins. In this chapter, we're going to consider how the global water cycle functions, particularly as it relates to the transfer of water between the Earth's surface and the atmosphere. As this slide points out, the total amount of water on Earth is neither increasing nor decreasing, although there are processes which continually generate or break down water, but these processes occur basically at essentially the same rate. For instance, when volcanoes erupt, more than half of the gases that are emitted during this eruption are water vapor. Concurrently, intense solar radiation entering the upper atmosphere converts, or what we call photodissociates, amounts of water vapor into its constituent hydrogen and oxygen atoms, which may escape into space. The relatively fixed amount of water in Earth is distributed among various reservoirs, as indicated by this particular slide. As you can see, the vast majority of water is found in oceans and ice sheets and glaciers. The atmosphere contains a very, very small portion of total water. However, small changes in the percentage of total water stored in the atmosphere have very interesting and sometimes very dramatic effects on the weather. The never-ending movements of water through and among various reservoirs on a planetary scale is known as the global water cycle, and this is a simplified diagram of the water cycle itself. As we can see, the global water cycle is a continuous flow of water and energy among oceanic, terrestrial, and atmospheric reservoirs, where evaporation, condensation, and precipitation are major processes which keep the global water cycle moving. This next slide shows a global scale water vapor image which shows evidence of long-range transport in the atmosphere above the Earth. We need to keep in mind that the sun drives the global water cycle. As we saw in Chapter 4, some of the radiation that strikes the Earth's surface is absorbed, that is, it's converted to heat, and some of the heat is used to evaporate water or sublimate ice and snow. If water didn't vaporize, there would be no clouds, no precipitation, and no global water cycle. In addition to solar radiation, gravity is an important player in that this attractive force keeps water molecules from escaping into space, as well as causing water to fall from the sky as precipitation. This slide talks about important processes in the transfer process relating to phase changes of water. We've talked about these previously, but if you need to review, please look this slide over. This slide shows us the percentage of annual precipitation over land that originally vaporized from the ocean, averaged over the last 15 years or so. We see that the greatest percentage of water is released along the coastal areas, whereas the least percentage of water, it seems to be released internally, and that would make sense as far as water and the cycle goes. This slide shows us the balance sheet for the inputs and outputs of water to and from the various global reservoirs, and it's basically called the global water budget. Over the course of a year, the volume of precipitation, that is, rain plus melted snow that falls on land, exceeds the total volume of water that vaporizes from land by about 30% or so. This is because over land there are certain precipitation forming mechanisms that are favored. Over the same period, the volume of precipitation falling on the ocean is less than the volume of water that evaporates from the ocean. Evaporation is more important because the ocean surface has nearly a limitless source of water vapor that it can deliver. So this slide indicates that the global water budget has an annual net gain of water on the continents and an annual loss of water, that's a net loss of water, from the ocean. Earlier we indicated that there was a balance between the loss and gain of water in the global cycle, so what's the story here? Well, to restore this balance and complete the global water cycle, excess water on land basically drips, seeps, and flows by gravity back to the sea through runoff, infiltration, etc. So it's the runoff component or the infiltration component which basically restores the balance and complete the global water cycle. As we saw earlier, the atmosphere also contains a quantity of water. Although very small, it's going to be proven to be very important. The amount of water vapor in the air is generally termed humidity, and we know that humidity changes regularly from hour to hour, day to day, season to season, etc. There are a number of ways of measuring humidity, like vapor pressure, mixing ratio, specific humidity, absolute humidity, relative humidity, dew point, precipitable water, etc. We're going to talk about a few of these and give us an idea what this means in terms of weather. Water's vapor contributes to the total air pressure, and we know that follows Dalton's law of partial pressures, and we call this contribution the vapor pressure of the atmosphere. One of the things that's important to remember about vapor pressure is as the water vapor content of the atmosphere increases, the vapor pressure increases. Water pressure is a highly variable component of the air, but composes relatively little of the atmosphere, no more than about 4% of the mass in the lower parts of the atmosphere. Other ways of quantifying humidity are the mixing ratio, the specific humidity, and the absolute humidity. As we can see, the mixing ratio and specific humidity are basically grams per kilograms of air in both cases, grams per kilograms. The absolute humidity is water vapor per unit volume of humid air, grams per cubic meter. These two numbers generally, when we're figured out, are very, very close together, and we consider them basically equivalent. Although this thing called absolute humidity, simply the density of water vapor, component of air, is fairly simple, it unfortunately has very limited application in meteorology, because we know as the volume of a parcel of air moves up or down in the atmosphere, air may cause absolute humidity changes to vary throughout, with absolutely no water being gained or lost by the parcel. So we don't talk about absolute humidity, mixing ratio, or specific humidity too much, but these are just other ways in which we can determine how much water vapor is in the air. Well, no matter how we quantify the water vapor in the air, at a specific temperature, we know that there is an upper limit to how much water can be held. At its maximum humidity, air is described as saturated with water vapor. We do know that there is a two-way exchange of water molecules at the interface between water and air, or between ice and air, and water molecules are in a continual state of flux between the liquid or ice and water phases. Whether we're evaporating or condensing, there eventually becomes a dynamic equilibrium that occurs in the atmosphere, in a parcel of air. So at some point in time, liquid water becomes vapor at the same rate as vapor becomes liquid. So at equilibrium, we can say that above a plane surface of liquid water or ice, the air is saturated with water vapor. The vapor pressure at equilibrium is called the saturated vapor pressure, and the mixing ratio would be the saturation mixing ratio, specific humidity at the saturation specific humidity, and the absolute humidity would be called the saturation absolute humidity. So these terms get somewhat confusing, but basically saturation is the key. We also know that changing the temperature has an effect on this equilibrium. Raising the air temperature increases the saturation, vapor pressure, and all those others we talked about, whereas a drop in water temperature basically brings about condensation, and this particular situation eventually ends up with less water vapor in the air at a lower temperature, although this is now in equilibrium as it was previously with a lower water vapor. Because temperature largely governs the rate of vaporization of water, the saturation vapor pressure, or the saturation mixing ratio, is actually a measure of the water's vaporization rate. These two graphs show us the variation in saturation vapor pressure, and keep in mind that means simply the vapor pressure at equilibrium with the changing air temperature. So if we look at the variation in saturation vapor pressure, we can see as the air temperature increases, the saturation vapor pressure in millibars also increases. Over with the mixing ratio, we can also see the same situation. Increasing the temperature increases the amount, that is grams per kilogram, of water in the parcel of air that we're looking at. So simply put, temperature increase means more vapor pressure, or temperature increase means more grams per kilogram of water in the atmosphere. These two tables confirm that That is, vapor pressure increases as the temperature increases, and the saturation mixing ratio increases as the temperature increases. If we're listening to a weather forecast, we don't hear too much about saturation vapor pressure or saturation mixing ratio. What we hear generally is, as frequently reported, the idea of something called relative humidity. Relative humidity compares the actual amount of water vapor in the air with the amount of water vapor that would be present if the same air were saturated. The relative humidity is generally computed from either the vapor pressure or the mixing ratio, and we know that at a constant temperature and pressure, the relative humidity varies directly with the vapor pressure or the mixing ratio. As one increases, so does the other, and as one decreases, so does the other. So again, to reiterate, at a constant temperature and pressure, the relative humidity varies directly with the vapor pressure or the mixing ratio. That is, the relative humidity increases as the vapor pressure is added to air, as long as the air temperature and the pressure remain constant. Here's something to remember. Because the saturation vapor pressure varies directly with the temperature, the relative humidity varies inversely with the temperature. If no water vapor were added to or removed from unsaturated air, the relative humidity increases as the temperature drops and decreases as the temperature rises. Look at the example that we have here. If we consider a clear sky and calm air or light winds, the air temperature usually rises from a minimum near sunrise to a maximum during the early afternoon, and then falls again through the evening hours. If the amount of water in the air remains essentially constant throughout the day, then the relative humidity will vary inversely with air temperature, and that's what we see here. Relative humidity is highest when the air temperature is the lowest, and relative humidity is the lowest when the air temperature is the highest. So after sunrise, as the air warms, the relative humidity begins to drop because the saturation vapor pressure increases as the air temperature rises. Another term that we hear frequently on weather forecasts is something called a dew point, the temperature to which air must be cooled at a constant pressure to achieve saturation of air relative to liquid water. So dew point directly measures the water vapor content of air. The higher the dew point, the greater is the concentration of water vapor in the air. Cooling unsaturated air at a constant pressure increases its relative humidity, as we know. When the relative humidity reaches 100%, the air is saturated, and the air temperature is generally the same as the dew point. Dew itself is really nothing more than tiny droplets of water formed when water vapor condenses on a cold surface, such as a flower petal on a clear, calm night, or on your glass of water that has ice in it, and dew forms or condensation forms on the outside of the glass. These maps show us the average surface dew point for July and January in the coterminous United States, and basically, as you would expect, In July, the dew points tend to be relatively high, and in January, relatively cold. Precipitable water is another way of describing the amount of water vapor in the atmosphere. Precipitable water is the depth of water that would be produced if all the water vapor in a vertical column of air were condensed into liquid water. We can see that the precipitable water is highest in the tropics and decreases as we go north and south. One of the things that meteorologists need to do is to monitor the water vapor in the air, and they do this through a number of instruments. These are all described in your text, and I'm going to let you spend some time looking those over. There are a number of YouTube videos which are associated with the course that you can look at to show how to use something called a sling psychrometer, which you can see a picture of in your text, and other types of instruments for collecting water vapor concentrations in the air. Water vapor satellite imagery is a very valuable remote sensing product for tracking broad-scale distribution and movements of water vapor, generally by way of infrared wavelengths that detect water vapor, as seen here. We know that as relative humidity approaches 100%, either condensation or deposition of water vapor becomes more and more likely. Condensation or deposition within the atmosphere produces these things we call clouds, so the probability of cloud development increases as the relative humidity nears saturation. We know that the relative humidity of unsaturated air increases when the air is cooled, the saturation vapor pressure decreases while the actual vapor pressure remains constant, or 2, when the water vapor is added to air at constant temperature. The vapor pressure increases while the saturation vapor pressure remains constant. We can say that expansional cooling is the principal means whereby clouds form in the atmosphere. This slide is a bit of a refresher regarding idiomatic processes that we learned about in Chapter 5, so you may want to kind of look those over as we go through the rest of these slides. That will help you out. Let's talk a little bit now about atmospheric stability. And we know that at a constant pressure, the higher the temperature of an air parcel, the lower its density. Parcels that are warmer, that is less dense, than the ambient air are buoyed upward by the denser surrounding air, whereas parcels that are cooler, that is, they are denser than the ambient air, sink. An air parcel continues to sink or to rise until it reaches an ambient air of the same density, that is, the same temperature. When we talk about atmospheric stability, we determine atmospheric stability by comparing the temperature change of an ascending air parcel or descending air parcel with a temperature profile, or what we call a sounding, of the ambient air through which the parcel ascends or descends. Let's talk for a minute about stable air. And this graph shows us a little bit about air stability. And we know within a stable air layer, an ascending air parcel becomes cooler, that is, more dense than the ambient air, and a descending air parcel becomes warmer or less dense than the ambient air. Any upward or downward displacement of the air parcel in stable air gives rise to forces that will tend to return the parcel to its original altitude. That is, it won't fluctuate up and down very dramatically. Keep this diagram in mind as we go to the next profile. Within an unstable air layer, an ascending air parcel remains warmer and therefore is less dense than the ambient air and continues to ascend. Whereas the descending air tends to remain cooler or denser than the ambient air, and it continues to descend. And this unstable air enhances vertical motion, and that's why flying through unstable air tends to be more of a problem in terms of the movement than flying through stable air. In terms of atmospheric stability, one of the ways that we determine that is by way of those things called soundings. We had it through radiosondes. Those big balloons we send up get the information back from the atmosphere, and there are a couple of stability terms, absolute instability and conditional instability, at which basically is related to temperatures and the rate at which the temperatures and the lapse rate occur. If the soundings indicates the temperature of the ambient air is dropping more rapidly with altitude than the dry adiabatic lapse rate, then the ambient air is unstable for both saturated and unsaturated parcels. This situation is known as absolute instability. If the soundings lie between the dry adiabatic and moist adiabatic lapse rate, conditional stability prevails. That is, the air layer is stable for unsaturated particles and unstable for saturated air. This is a relatively common situation where unsaturated air must be forced upwards in order to reach saturation. But once saturation is achieved, the now cloudy air cools at the lower moist adiabatic lapse rate. Within a neutral air layer, a rising or descending air parcel has the same temperature and density as its surroundings. Hence, a neutral air layer neither impedes nor spurs upward or downward motion of air particles or air parcels. After analyzing a sounding, and depending upon the data we receive, the atmosphere is either stable or unstable, and the soundings are coded A through E as shown here in this particular diagram. Stability conditions for each of the 5 sample surroundings are summarized in the table below the diagram. This is a Stuve diagram, and it is basically used to permit the evaluation of various atmospheric processes which and data which has been received from radiosondes and then graphically demonstrated on this particular Stuve diagram. Coordinates on this diagram consist of the temperature in degrees Celsius and Fahrenheit, increasing left to right. We also have pressure in millibars on the right vertical axis, decreasing as we go up, as you can see, less pressure as we ascend. Also marked on diagrams are altitude in kilometers and feet, which correspond to pressure levels based on standard atmosphere. The straight red lines slanting from lower right to upper left are the dry adiabatic lapse rates. By plotting a sounding on a Stuve diagram, this would enable a meteorologist to determine the stability of various layers within the atmosphere and assess the potential for deconvection and cloud development. Meteorologists also use plotted values of saturation mixture ratios, the slanted black lines we see here, in grams per kilogram to determine relative humidity and saturate levels of rising air parcels. There are a number of YouTubes also found in the course that give you some help with appreciating this particular diagram. I'd encourage you to look those over. There are several things that cause air to rise, or what we call the lifting processes, and they are the ascending branch of a convection current, or sometimes along the surface of a front, or possibly up the slopes of a hill or a mountain, or where surface winds converge. All of these may cause the lifting process. This slide describes the lifting process relative to the meeting of contrasting air masses, that is, as in a front, cold and warm. In orographic lifting, winds ascend along the windward slopes of a mountain range and descend along the leeward slopes. The climate is generally wetter along the windward slopes than on the leeward slopes, as we can see by this diagram. An orographically induced contrast in precipitation is apparent in the Pacific Northwest, where the north-south trending coastal and Cascade ranges of mountains intercept the prevailing east to west flow of humid air from the Pacific Ocean. We can also talk about convergent lifting. When surface winds converge, there's an upward motion that leads to cooling of this air parcel, increasing relative humidity, and possible clouds and precipitation. Converging winds are largely responsible for cloudiness and precipitation over a low pressure area. This is seen a lot in the Florida with its very high frequency of thunderstorms due to these convergent lifting processes.